How you guys doing? Last day of the conference? Pretty good? You all made it? Are my friends from Ohio here? No? No? Okay. They didn't make it. What? Just give me a sec. I haven't actually spoken to it. Oh, can you just All right, so last day before lunch, as you know, lightning talks. That's what's happening next. And according to the program, we're going to start at 9, but I don't have a 15-minute introduction or anything. So I think, what do you guys think? Should we start a little bit early? Yeah. Oh, okay. So, but you'll get your laptop back, Phil. So quickly about the format. So we originally had intended, about 7 minutes, and then that equates to about 20 slots. But you can see we actually have open slots. So this one isn't open anymore. So we have 4 open slots. But so is there anyone who how about like last minute lightning talk? I mean, it could be basically anything. You don't need slides or anything. What do you think? Come on. Marcus. No, it's not. Okay, so we have Marcus. That's good. I need to. I can only edit this from my phone. So Marcus, anyone else? Was that the business model talk, or was that actually so serious? Okay, 5 minutes on radio schedule. That's cool. No one else? Yeah, I might actually just do one myself, but I'm gonna also have to organize, run the show, and then if I can put something together. But the bottom line is that we don't really have to be sticklers for time. Then it's not like I actually have to throw you off the stage after 7 minutes. I do.
Otherwise, they'll go on forever. Yeah, I think you're gonna have to keep it pretty.
So I don't have to keep it to 7. I'll keep it short. But yeah. But I'm assuming that the speakers who are on this list already know this. So yeah, this is the only. I'll just look angrily from this table. What? It's impossible. All right. So this is the list of talks. If you're on this list, please sort of remember your relative order, because it's the one thing that's a little bit awkward is we don't have the presentation laptop here. So and also even if we had, we'd have to like unplug and replug it every every 7 minutes. So this is the order that it's going to be in. So please remember your relative position on the deck, and then there'll probably be a little bit of the scheduling will be a little bit dynamic, probably like the radio scheduler is. So I can't actually give you a time right now, but you can sort of figure out if later, if you need a bathroom break or something, you can probably figure it out yourself if you have time to do that. Finally, if you want to show some slides, that's fine, but you have to bring your own gear. We have VGA and HDMI only here at the front, but we do have an audio drop, so that's all possible. But any time it'll take you to punch in the correct X-render command line will come out of your slot. So make sure that you can actually connect your laptop to a projector in time. And otherwise, as I said, if you have an idea for a talk while this is going on, that's also fine. Just approach me quietly here at the front. It should be kind of related to SDR, but there's no hard rule. Just make sure it's appropriate and stay clear of awkward political issues or something like that. Actually no. What the hell? And yeah. So I'll look at you angrily if I think you're going on too long. But if you go a bit longer than the 7 minutes that we are. Oh, I don't. I don't know if I'm yet awake enough to do that actually, but oh God. All right. Any questions before we head in? Oh, thank you. That's the other thing. Yes. So for those who you can disconnect. For those who don't have a ham radio license yet, after today you have no more excuse. And tests have already started, basically. So we have, what did Phil say, like aging white dudes or something? On the boat right now, taking exams. So if you're not an old white dude, even better, then you can sort of help, unskew the demographics. That's the word. Man, it's unweighted demographics. Yeah, come on, unweighted demographics says the old white dude. But for real, even if you haven't studied yet, go to hamstudy.org. Give it take a look at the difficult questions for the next hour or so, and then just show up at the boat, take your exam, and because if you don't, we will make fun of you after today, because that's your last chance to get away without a license unscathed. There you go. And the actual test will not take you long. You might have to wait for a judge to do the paperwork afterwards, but the actual test is sort of with order of like 10 minutes maybe, if you're thinking about it. It's not difficult. So I highly encourage everyone to do that. And even if you're a foreigner, you can take an American license, and some countries will let you will give you a license of their own if you can prove that you have an ARL approved license without having to take the exam. So so Germany is very awkward to actually do the exam, because you have to show up in the middle of the night at some random location. It's very complicated. But they will actually, if you have proof of an FCC approved extra or general license, they will actually give you the German license equivalent without having you to take the exam. So really no reason not to do that. And it's just fun. Okay, what the hell. So first presenter of the day was someone from Edis. I already have the table no longer in front of me. It's Tom. And then I think we have two more Edis guys, because I think the table was just sorted alphabetically by company or something. But that's fine, because the actual topics are very different. So while Tom sets up, I'll quickly reiterate. If you've forgotten your relative order on the table, I'm right here. You can just come up and ask me. If you need to swap for whatever reason, same thing. Just come up and ask me about it. Yes? I'll try and get that doc shirt. Okay. Can we put it on the website, maybe? Oh, IRC? Yeah. Radio Slack? That's a good idea. I think I can edit it, so I might have more privileges or something. All right. Are you ready, Tom? Can you? You have slides. I'm ready. All right. Take it away. Oh, wait a minute. You have a clip-on mic down there, but you can also use the,
Are you on now? Okay, I got that. All right, my name is Tom Tsou, Edis Research Software Engineer, and one of the judges among Edis Research and Xilinx on the RFNoC and Vivado HLS Challenge. Next 5 minutes, I'll just go over some of the criteria we used in judging and how we arrived at a winner this year among our 3 finalists. So let's get going. Criteria. Internally, we had a much larger scorecard than we have here, but really, looking at the tallied up scores and what we looked into, they really fell under 3 categories. Challenge, how difficult was the project? Functionality, does it work? Implementation, and in this case, really, we look at the code. So this is an HLS challenge, so we consider coding in the sense of HLS design, feature use, and more general categories of coding, readability, maintainability, and also, to some extent, scalability as well. So given that, let's go. Number 3, our 3rd place winner, Team WinLab, channel sounding. What we really liked across the board on this in the scores was the fact that in this case, we had a design that came out, that was implemented, and taken all the way through execution in terms of research. It was a research project, and it actually got deployed. You can see the robot down there, and this one was actually used to collect data, and really they took it all the way through. Where the scores weren't quite so as high when we look at the complexity and difficulty here, channel sounding, mainly on the correlator side, was not quite as challenging as some of the projects we'll see next. So that next project, we see a pretty big jump in terms of the challenge here. ATSC, video decoding. I work in standards, 3GPP, as anyone else that works in standards knows that it's certainly never a simple task. So certainly a good challenging topic there. Where we saw on the score is a bit more mixed scoring was the fact on the HLS use and the code itself. As many of you may know, there's an existing GRATSC implementation, and the approach was really an interesting one, I thought, to basically shotgun code through that existing C++ code and run it through HLS and generate Verilog FPGA implementation on the way out. The approach to basically use the existing code, in some sense, was really showed capabilities of what you can do with HLS. On the other hand, some thought that that approach, as far as using HLS features, design, and how that would scale, some saw that approach as being a little bit more mixed. And with that, we have our winner here, E.J. Kreiner, who we saw a presentation earlier this week on neural nets. And what we had here is a really exciting area. Certainly we see the buzz, the hype, if you will, neural nets, but that by itself wasn't taken into account. But when you add RF to it, working I and Q samples and neural nets, we start seeing an area where exactly where the difficulty and the applications are not really well defined. So certainly good points on that in terms of challenge. But really where we saw the big separation here as far as the scoring came down again to the code on the HLS side in terms of design, the implementation, the readability of the code, and being able to possibly take that code and even take it into another project or hand it over to another developer. So that was really the deciding factor as far as really separating the final scores of our winner here. And with that, it's lightning talk, so that's all I have. On behalf of Edis Research, National Instruments, Xilinx, judges, certainly congratulations to EJ, our winner, and all of our finalists. Thank you.
Take questions. We have time for questions. Yeah.
Yeah, I mean, I think given the fact that this is certainly our first time doing this, so given the range of projects that we received, it was we left it pretty wide open. And in the end, we had a pretty wide range of approaches in terms of how the code was done, be it experimental project standards. So that, the diversity of projects was certainly very exciting. And I think from a judge's side, it was really interesting to read and look at those submissions. I do encourage you to see, we did have the finalists do YouTube presentations. I encourage you to take a look at those, especially the ATSC one those were quite fun. Those were quite fun and entertaining. So I think if you look up a RFNoC challenge videos or something like that, I do encourage all of you to take a look at those.
Thanks. Anyone else? Okay. I don't know, Brent, are you still getting set up? There we go. All good. Yes, this is virtual.
All right, well, hello. I'm Brent Stapleton from Edis Research, and here to talk about the new UHD Python API. So this was released a little while ago. Some of you may have seen the email Martin sent out on the GNU Radio and UCERT mailing lists. So it's a new Boost Python API to wrap the C++ API. Its goal is to have a full API exposure, although we're not quite there yet. It's still in development. It's also a separate API from our GRUHD. It doesn't use the same SWIG interface. It also has some other differences. So we expect very few cases where you're going to mix and match those two. It's a separate branch on our public repository right now, so feel free to take a look and let us know what you think or any improvements that you want. We have an issue on the issue tracker for questions, comments, concerns. So just a few heads up things right now. The multi-threaded performance isn't quite there. We have plans to improve it. We actually have an active discussion going on in the issue tracker regarding that. Furthermore, the Pythonicity has been scrutinized a little bit. I, for one, really like the PySDR UHDs, keyword arguments in their functions. So perhaps that's something that we would want to do as well. Still, something we're thinking about. Also, the documentation, we're still working through that, and it does not support RFNoC yet, although that's certainly a planned improvement. So I just have a quick demo to go through, show how easy it is to use. So I have a IPython notebook. I guess I can just have that open. It's an easy tool for me to use to rapidly develop Python applications. We have some pretty standard imports here. This is the instantiation. You can see on the terminal, some pretty standard UHD logging right there. And then this is really the function that a lot of you will use. It's a convenience function that has some standard UHD function calls wrapped up in that. So we do that. You can see that we have some UHD logging, and then we can do cool things like run matplotlib in an IPython notebook and get out a figure. That is the spectrum with this little antenna in B210. Just something to help. You may want to use this usurp none to help the destructor in Python, so it's garbage collected a little faster. And then, your usurp will then be accessible, unclaimed on the rest of your device. That's really all I have. Thanks for listening. Any questions?
Do we have any questions? All right. Neel, you can get set up. And after Neel, we actually have two talks by Joshua from LimeSDR, so you can get your stuff ready. Neel, I don't think I've ever seen you give an actual presentation that was not an introduction. I'm standing right here. This is a unique event. So Neel is also one of the cyber spectrum organizers, in case you didn't know, and he gave one of his fantastic introductions yesterday. And he's also a very skilled imitator of accents. And of course, Neel's also the captain of support. So if you're a USRP user, then you probably actually have interacted with Neel. So this is your chance to get his autograph. If you have black slides, then it's perfect.
Okay. Okay. Okay, well, good morning. Hello, everybody. I'm Neel Pandeya. I'm the support manager at Edis Research, and I just wanted to go through the support model and show you the knowledge base and make sure everybody was aware of it. Let's see. So the support model at Edis usually is through email or the mailing list. If you haven't seen, we have a mailing list, and I'll try to bring that up here. Geez, how do you? Oh, I can't see. Can you change the screen size on this? Jeez. So there's two mailing lists. There's USRP users and Discuss GNU Radio, and those are the primary mailing lists we use. So depending on the nature of the problem that you have, if it's something related to the USRP itself, the hardware, or the UHD driver, we usually suggest you use the USRP users mailing list. If it's something specific to GNU Radio and the use of GNU Radio on USRPs, then you can use the Discuss GNU Radio list. And hopefully you would agree there's a large community of people who are willing to help, not just Edis people, and people are pretty responsive and helpful on the mailing list. The other way to get help, technical support, is through a direct email, and simply email support@edis.com, and we'll get back to you. And if you wanted to keep your conversation private, that would be the way to do it. You can email us directly, and whatever we discuss is confidential between Edis Research and you. There are some support resources. There's the user manual. Probably most of you have seen this before. And this is installed locally when you install UHD, so you have a local copy of this. And it's also online at uhd.edis.com. This is more of a reference, but it has a lot of technical information and sort of a programming reference type information. And the thing that I wanted to highlight today was the knowledge base, which we launched about a year ago. And I want to give a special thank you to Nate Temple, because he did a lot of work on this and was really key and instrumental to putting this together. And on the knowledge base, we have getting started guides, which will walk you through some introductory steps and reminders and tips for pretty much all the daughter boards and motherboards, all the products, as well as RFNoC and the octoclock. And then we have a section for hardware resources, which has information about each device, such as its specifications, schematics, key components, data sheets, FAQs, in the case of the X series and the N series, DSP, FPGA utilization information, and so on. So it's kind of like an encyclopedia of information on the device. So if you have questions about things, you usually can find the answer here. And then there's a software resources page where we list, let me try to minimize this. I can't see the other part of the screen, but well, anyway, there's a software resources page as well, where we have a guide on RFNoC, as well as other third-party softwares that run on the USRP, like cellular stacks and such. And then there's the application notes section. Oh, okay. And we have about, I don't know, 20, go ahead. I know. Yeah, thanks. And we have about, 20 or so odd application notes here. Whoa.
It's showing something else.
Yeah,
it's
which tablet?
Oh, what did you do? There you go.
Okay. So we have a whole bunch of application notes here that cover different topics, like how to build and install UHD on different operating systems, and some examples, and so on. And we're adding a lot of application notes over the next 6 months, so you'll see a whole bunch of new content. I'm hoping we can add maybe 15 or 20 application notes to cover different things. We have, if you have any ideas for application notes or any content that you see that's missing, please let us know. We'd love to hear from you as to how to expand and enhance the knowledge base. Just a survey, how many people have actually used the knowledge base or know that it exists? Oh, okay. Some of you, okay. That's about it. That's pretty much it for my talk. I just wanted to highlight, really the key thing was the knowledge base. So any questions? Okay,
You can
thank you.
start setting up. Yeah. I think there was a question. Oh, there's actually.
Oh, yeah, go ahead.
Yes, I know there was some discussion when you first rolled out the knowledge base because there was some performance USB chipset information on your old site before you switched to the knowledge base that didn't get carried over at first. Did you guys have an update to that, or
Yeah, we're
hardware
working-
that works really well?
Yeah, we're working on updating that. The old one was really out of date, and so we took it down, and we just haven't had time to update that and put up a fresh version. So it's coming. Yep.
Anyone else?
This is, I have two back-to-back lightning talks. That's more like a slow, rumbling thunder talk. Do you have anything yet? No. There we go. Okay. Hey, I'm Josh Lifton from Crowd Supply. These talks I'm actually speaking on behalf of LimeSDR. I've worked really closely with the Lime Microsystems team for a number of years now, helping them crowdfund some of their stuff. I'm going to kind of give a primer about open hardware and how it's perfect for crowdfunding. So this is what a computer used to look like. And back when these were shipping, they came with these wonderful schematics, and it was kind of meant to be taken apart and put back together again. And of course, that's sort of mentality is long gone from most consumer electronics, certainly from personal computers these days, which was kind of the inspiration behind this computer. This is the Novena open source laptop by Bunny and Zobs. And it's not meant as a consumer product by any means. This is actually the back of it. The front is the screen, just opens in reverse, and it doesn't have a keyboard built in. You just use an external keyboard. And it was built by them to be the tool that they wanted to use, right? So it's not only a laptop, it has an IMX6 processor in it, but also on board has a Xilinx FPGA, I think it's Spartan 6 on it. And a bunch of other goodies that you wouldn't expect on a laptop, like two Ethernet ports and a bunch of breakout pins and whatnot. So it's kind of this hacker toolbox of sorts, and they use it in their work, and they've built derivative tools on it. But they raised close to $800,000 on Crowd Supply, and we helped them do that. And that was kind of a good proof point that led the way in showing how open hardware can come into actual being. So a little bit about Crowd Supply. We're a crowdfunding platform. We focus on open hardware. And the thing that we're most proud of is just that everything that's been funded with Crowd Supply is actually shipped to backers. That's the 100% delivery rate. Nobody's actually gone off and completely misspent the money or flown the coop. And we've maintained that for over 4 years now, so I'm pretty happy about that. Our average raise is $64,000 or a little bit more maybe now, and that ranges from a couple $100s to well over $1 million in projects. So it really can fit any sort of project. And finally, the percentage of projects that launch and then achieve or surpass their funding goal is right now about 61%. And that's about as high as I'd want it, honestly. If you're not failing a bit, then you're not doing anything interesting. So I'll give a little bit of advice. I have a lot of advice about crowdfunding, but the stuff I want to get to everyone now is simply that what it is and what it isn't. It's not free money. It's not a new way to market your product, and it's not a shortcut by any means. It's just as hard to do all of those things as it's always been. And the free money part is especially important, right? You're actually going into debt. You're taking on debt, essentially, to your customers, and debt in both the financial sense, but also the trust sense. What crowdfunding is great for is kind of a source of capital that, of course, you have to pay back in the form of sending a product. It's great for market validation, and it's great for building a user base. And when coupled with open source and open hardware in particular, it's a pretty powerful thing. So there's a difference between open source software and open source hardware, of course. You can kind of think of open source hardware as the superset of open source software, and there's plenty of firmware and host-side software and drivers and whatnot that's code that goes into open hardware. But fundamentally, from where I stand, the difference is largely one of cost, right? It's very cheap to shuffle bits around. It's very expensive to shuffle atoms around. And that's the difference between a repository and a manufacturing line. So it's a natural fit for crowdfunding, both because hardware needs money, but also because open hardware needs a base of support, and that's the whole point of crowdfunding. So give a couple examples of projects that we've launched on CrowdSupply as a way to illustrate this car mechanic trilemma. And that trilemma is simply that there's good, fast, and cheap, and you can pick two of those things. So if you pick fast and cheap, then the example I'd point to is actually the laptop I'm using right now. It's called the Librem 13 laptop. It's a consumer-grade laptop. It has a modern processor in it. It's an Intel processor. And it was designed, all the components were picked such that you wouldn't have to run any binary blobs or kind of mystery firmware at all. It itself is, the schematics are not open source or anything, but they're working on that. It raised, between it and its brother, the 15-inch laptop, raised over $1 million. It's not necessarily good, though, because it's still running an Intel processor. Good here means free and open source, right? So there's still the Intel management engine, and that's an inescapable fact of modern life when it comes to personal computers. So if you pick good and cheap, where you want something completely Libre and inexpensive, and I should mention that the Librem 13 is roughly the same price point as a comparable laptop, so it's $1,200 or something like that. So if you pick good and cheap, you're going to neglect fast, and that's what the EMA 68 project is. This project raised a bit over $200,000, and it's centered around that little card lying on the table in the lower left. For those of you who had laptops in the 90s with a Wi-Fi card, it will look familiar. It's a PCMCIA form factor, but it's completely repurposed. It's just the case and the pinout. But inside is a full-blown computer based on an Allwinner A20, I believe, in this version. And that's the whole point, right? This version is the A20, but the next version might be a higher processor, a higher power processor. So you want to just swap out the card and not all the other hardware like the display and the keyboard. And so that laptop there you see is actually 3D printed. The little wooden case next to it is a docking station for a desktop. But of course, it's not fast at all. It's a very slow computer. Still run Office or OpenOffice and a browser and whatnot, but you're not be doing CAD on it. And then finally, if you just go for as Libre as possible and as fast as possible, you of course end up with a very expensive computer. This is a render of the Talos workstation, which is an ATX board, raised over $500,000, but actually failed to meet its $4 million goal. The entry point for this for a full working computer was about $17,000, which is actually a steal compared to its competitors in that same space. If you're doing AAA game development or serious engineering CAD on it, that's what it was designed for. It would totally rock that. So that's kind of the personal computer realm, but there's a bunch of other things that you can do with open hardware instead of just computers. And it seems kind of insurmountable, that trilemma seems insurmountable, but I'd argue, and as Bunny argues, he's the guy who made the novena, that Moore's law, because Moore's law is slowing down, it actually is a point in favor of open hardware, simply because there's more time now between iterations, between hardware iterations. And in that time, we can build robust ecosystems that are open and can support a community. So instead of computers, what else would we use open hardware for? This is an example. This is called the Signet. It's a hardware password manager, little USB dongle, completely Libre. And it kind of gets at the core of what open hardware, one of the killer apps, I think, of open hardware is just security, right? Information security. So this is a completely auditable piece of hardware that holds all of the little bits and pieces that tell you the difference between the real world and the dream world, right? Now, of course, that needs to be based on open silicon, because even if you have a microprocessor in there, you still can't fully trust it unless you know what's happening at the lowest levels, and that's RTL and below. This is the Open 5 processor, which launched on Crowd Supply. Unfortunately, it failed to meet its goal. It's a pretty ambitious project. They're still working on it. But it is arguably the very first completely open source microcontroller. Not just the core, but also the peripherals. And that's key, right? Because making cores is relatively easy. Making analog domain peripherals and buses is rather difficult. This is a close cousin. This is the Sci5 FE310 chip that's been put onto an Arduino-compatible board. And this did fund, and we're selling these chips right now. So this is, Sci5 is dedicated to open silicon. Of course, in this case, it's just the core. The peripherals aren't yet open, but they're working with that Open 5 team I mentioned earlier to open that up. And we just started selling the actual chips on these as well. So if you want to develop your own product around these chips, you can now do that. So I'm going to segue into LimeSDR stuff in particular now. But before I do that, if you're interested in crowdfunding some open hardware or just finding out more about it, I'll be around today, happy to chat. And of course, you can take a look at the website. So LimeSDR, we launched the first LimeSDR board, I guess it was over a year ago now, about a year and a half ago. And it's based on this LMS 7002M chip, and we were pleased as punch that we got our own special logo on a small batch of those chips. They're all gone now, but that was a nice token. So here's some of the projects that the Lime Microsystems has launched with us. This is the one that launched just yesterday, I believe. This is LimeSDR Mini. It's the newest member of the LimeSDR family, and it's really meant to be the most accessible one yet. I think all the $99 units are sold out now, but it's just over $100. Has the same chip as the full-sized LimeSDR, 2 channels. And this is a prototype, of course. It will have, instead of these 4 connectors, it'll just have 2 SMAs. And instead of this fan, it will have a heatsink. There might be a couple other small differences, but otherwise it's fairly nailed down. You can go right now to, let's see, take out your wallets and go here. This is the web page. Find out more details about this. It's fairly competitive in terms of feature set, has some accessories. I'll let you browse that. Oops. So now Lime, in working with Ibrahim and his team at Lime Microsystems has been really great, first of all, but it's really opened my eyes to what's happening and their vision for RF. Which is basically an end-to-end solution for democratizing wireless, right? Right now, the situation, if you're looking for open wireless, for various definitions of open, is fairly bleak. There's really no cellular solution that's widely deployed. It's hard to get into. There are a lot of obstacles for the sort of innovation that software enjoyed and on which the internet is built. I think what they're doing is approaching this from that perspective. What can we do to make it a much more fertile ground for innovation? And their answer is essentially to hit every pain point along the way, right? It's the hardware, the software ecosystem contributing to that, the community. They help run Myriad-RF, which I believe Josh Blum is going to talk a little bit about. Yay. And then, so it's not only the RF hardware, but also the kind of the commodity, quote unquote, commodity hardware that would be the host side of that, right? So this is this middle slide here is the LimeNet network in a box. And it's really is just commodity hardware that they've specialized, picked and chosen to be compatible with the LimeSDR family. So you know that out of the box it's just going to work and will work to spec. This is the original LimeSDR in one of their aluminum kits. Here's outside of the kit. And the nice thing about this, they have these boards which are meant to be widely distributed, like this LimeSDR, which we've shipped thousands of those already. And then there are these more specialized ones, like this PCIe board, which is essentially the same thing, but just higher bandwidth to the host machine. And they keep iterating on these. So here's the LimeNet, kind of the highest end LimeNet network in a box machines. It's a powerful gaming PC with a chassis that has the power amplifiers and antennas. So it really is just a cellular base station you can drop down and start using right away. And of course, here's the prototype of the Mini. So that's Crowd Supply and LimeSDR and Lime Microsystems. It's been a pleasure working with those guys. I know they've had a big presence here over the course of the conference. I'm sorry I missed them. I just flew in last night. But yeah, check out the LimeSDR Mini and the other LimeSDR family products. And I'm around if you have any questions later in the day. Thanks.
Yeah, you can give a round of applause. Is Josh actually here?
Yeah, he's right there.
Oh, right in front of me. You can go set up. I don't know. Is there, if we have some questions, this would be a good time to ask them while we're switching laptops. None. Okay. All right. Okay, well, probably take a minute to, yeah, just go ahead. And people have asked me if they can do last-minute additions, and absolutely, yes. We still have slots open, so yeah. Mm-hmm. Oh, okay. Was that a yes? Yeah. Okay, we're still working on that guy. We can see slides, yeah. I think they're sort of cropped a little.
Worked on yesterday's projector.
There we go.
Well, if it looks okay and it fits on the screen, I'm happy.
We're happy to. Go ahead.
Thank you. Mike, 1 second. All right, testing. All right, that looks like the first page. Well, hello, I'm Josh Blum. Lime Microsystems invited me here to talk about open source work, driver options, and LimeSDR support. But I'm also here representing Skylark Wireless, my day job. So, billions of people worldwide don't have access to internet. In the US alone, 50 million Americans don't even have broadband. Fiber, cellular, satellite, dial-up, Wi-Fi technologies are all either too slow, not scalable, or cost prohibitive. Skylark Wireless is a startup spun out of Rice University in Houston. Our goal is to bring broadband to rural and underserved areas using multi-user MIMO technologies and our unique platform. Pictured as a chain of iris radio nodes. When you think of an iris, think of an eye. Many eyes, many antennas. Perhaps you got a chance to see the iris nodes and various daughterboard options at the Lime Expo booth. Each iris consists of a dual-channel RFIC from Lime Microsystems, configurable clocking, optional gigabit Ethernet, and a Zinc FPGA for high-rate streaming, signal processing, and management. Iris nodes are chainable. Our uplink and downlink connectors allow for the distribution of high-speed serial data, clocking, synchronization, and power across the chain. Iris chains can grow indefinitely because the inherent mathematics of beamforming, mainly multiply accumulate, although additional power injection is required. And further, our base station backplane supports multiple chains of irises to form an antenna matrix. Irises are flexible. A reusable radio design with custom daughterboard options allows us to cover different bands of interest such as CBRS and white space. The Iris radio module can also be used as a standalone endpoint and for other SDR development purposes. It works out of the box with SOAP SDR and GNU Radio. Individual nodes in an Iris chain are all IP addressable too, using custom packet switching in the Zinc FPGA, done by me. Each node can be individually streamed from using gigabit Ethernet or the higher throughput backplane. Building on irises, we have created an extremely dense, affordable, and scalable matrix of phase-synchronized radios. If you are interested in channel estimation, beamforming, or direction finding technologies, please contact us. We are a contract manufacturer. We can produce custom front ends, clocking, and synchronization options. We may have a system for you. And of course, this is the perfect crowd to ask. If this is the kind of work you'd be interested in, please find our jobs page. Skylark is always looking for talented wireless engineers with coding experience. We're looking forward to some big announcements in the near future, so I'm afraid that's all I have to say for now. Take a look at our newsfeed or contact us for more information. Thank you for watching.
Any questions? And is Robin here? Oh, there we are. You can go set up, and people can ask Josh questions in the meantime. No, don't keep it. Leave it. Looks like there's no questions. Okay, Josh, do you need help? No. Robin's a pro. Why did I even ask?
I've been having problems with my laptop. You pick it up by the corner, the motherboard flexes, crashes.
Don't pick it up by the corner.
Oh, the only thing I forgot to bring up was my phone. You'll have to tell me when 5 minutes is up. Thanks. I knew you would. Let's see. There we go. So for those people who didn't hear, for students who are attending the conference, we are taking down names and we'll be shipping you Plutos if you'd like. Just come find me sometime later today. Just to talk a little bit more about Pluto and a little bit more details for those people who haven't seen it. It is just this sits in your hand, 99 bucks. It is based on a Xilinx Zinc. It is cross-platform. It is based on IIO. So IIO is actually pretty interesting because from a host library perspective, the library that runs on your PC, you can develop your software there and then actually get it to run directly on the device with only making a single line of code change. Instead of connecting remote over USB or connecting remote over IP, you just say connect local and everything else is exactly the same. So to talk about a few use cases, the typical one is connect to host, but because we are actually running Linux on here on a Zinc, you can actually connect to a thumb drive and run scripts off the thumb drive that controls the radio, capture files, play files with no PC, with just like a USB battery or a USB solar device. Because about the current consumption on the device is about 400 milliamps, typically. You could connect it over Wi-Fi, and people are already doing this. People have taken the dump 1090, run it directly on here, and then actually transmit the ADSB packets directly over Ethernet to wherever they want to on the network. You could connect it up to Wi-Fi, so we support the typical Raspberry Pi Wi-Fi dongles and USB dongles, and you can power this from your car cigarette lighter adapter to drive around with it if you want. And there's some folks that have already modified the kernel, support USB audio, put FM radio decoder on here, and they can plug USB speakers into it and actually play FM. So there's all kinds of things you can do with it that are untethered as well as tethered. And I think that's actually where the more interesting radio pieces are kind of like driving towards, is not just radio attached to a PC, but it's a radio working by itself as an embedded device. And I just wanted to talk a little bit about the embedded aspects of things. So it's totally open schematics, open layout, open firmware, which means open HDL that you can use with Vivado Webpack, which unfortunately isn't open, but it is zero cost. It is the open Linux kernel, open user space based on build root, open host drivers, open host libraries, and to build the firmware, it's just git clone, export a few variables, and then type make. And it'll build everything you need, including all of those things. So it's actually pretty easy. And then you can see this is just a GIF I made of the layout. So to help facilitate development, it normally reboots to Flash, where it boots a fixed U-boot image and then loads a Linux image, which will include the kernel, the bit file, the RAMFS, and then boots it. But you do have options to do device reboot, to boot to serial flash, to actually load an image into RAM and then boot from that, rather than committing to Flash when you're doing development and you want to see how things are going. Verbose, break, you can halt or stop in U-boot, that kind of an idea. It does support Linux, Mac, Windows. It comes up as a composite device. So you plug this in and it'll show up as a libIO device, as a mass storage device. So that's actually how we do normal firmware upgrades. So I plug this in, it shows up as a hard drive. When I want to take a new firmware image and put it on here, I just copy the file to the hard drive and click eject, and it'll start writing it to the flash, which is pretty cool. So we look at this as like, hey, this is actually a great example just of a cool embedded Linux target that you can take and reuse some of these concepts from. It shows up as a USB serial and also Ethernet. And Ethernet, because we use RNDIS, which is a Windows-supported and Linux-supported environment. It's not natively supported by Apple. They have their own thing for iPods. But there is actually a kernel module for Mac, which is called Horrendous. And Josh Wise, who does it, which is awesome, he's actually looking to get back his real life, because everybody with an Android phone and wanting to connect it to their Mac tries to use this thing, and he's looking for a new maintainer. So if you're interested in doing that, that's totally fine. For support, we have our engineer zone. There's some guy somewhere else that's not affiliated with us who started up PlutoSDR.com, where he's running his own forums, which is awesome, except he's using our logos without permission, which is not as awesome. But if you ask questions on there and don't get an answer, that's not our fault, because we don't actually watch that. But development, there is a JTAG to serial adapter, so you need another little $50 little dongle if you want to hook up JTAG, and you can do debugging with the Xilinx tools or connect to the serial port and those kinds of things. Now you just usually have a device or two with a little ribbon cable hanging off with this little device hanging off of. Things people are doing, like the dump 1090p, streaming right out Ethernet, and that's, so I can, plug this. I always try and do demos on Windows, not because it's our preferred platform, because it's our least preferred, least tested platform. So as soon as it boots up, Linux will start blinking the LEDs in the back. I've been told by a few people that we have, the LEDs are too bright, so we might actually tone those down a little bit. But some of the things I can do is, I can actually take a putty. Oh, let me do this. See if this works better. Yeah, okay. So I can just SSH to 192.168 2.1. And I say, yep. And I can log in as root, and the password is analog because we're super narcissistic. It's an easy name that everybody remembers. And I can, uname -a, and there's the Pluto device, and it is Linux. I can I can run IO info on here. I can see all the devices, just like I would on my host. I can run top. I can see, IOD is running, the Avai daemon, with the load average of basically 0. So when the device is running, when it's doing things, it's super not loaded because we've tried to optimize things so it's almost 99% DMA and just basically managing interrupts. So you basically have a 600 megahertz core to run whatever you'd want to on it. Does anybody have any questions? Okay, thanks. I'll switch. Oh, let me show you this. So this is the PlutoSDR.com. Yeah, I have no idea who this guy is. But people are asking questions and doing cool stuff, so which is awesome. So because I couldn't do the corporate spiel at least once during my all the GNU radio presentations. Oh. Is it? Oh, it's not up on this screen though. There we go. Just a little bit about analog devices. So we work with our customers to try and make not only our products but their products disrupt the market. So that's why we do things that nobody else can do, like 100 megahertz of bandwidth of RX and 250 megahertz of bandwidth of TX with DPD in it, like Sham talked about on Monday. We work really hard with our customers to leverage over 50 years of experience. So analog devices has been around in the semiconductor business since 1968, which is a very long time for any semiconductor company. We actually started out making modules and then got into the IC business. So us continuing to do modules, continuing to do systems in package, these kinds of things is actually pretty natural for us. When we look at what's kind of going on, we have our core technologies of sensors, measurement like data converters, clocks, amplifiers, power, connection, RF transceivers, microwave, millimeter wave, things that can interpret like DSPs and processors. We've added on that with acquisitions over the past few years, like Analog Devices purchased Linear Technologies, Hittite, and Innovasic. So now we have things like real-time Ethernet, 110 gigahertz RF platforms, as well as an entire portfolio of a much more broader portfolio of power. We've also been kind of adding to those things in the platforms, where we've acquired like Snap Sensors, Cypress Security Solutions in Florida, Vescent, and many other things because people want to make sure that they can ask one person the entire question from the sensor to the cloud and beyond. And from an analog devices perspective, for us to be able to answer those questions and optimize chips for 2 years from now, we need to understand that better or almost as well as our end customers do. And innovating, keeps customers ahead of what is possible, which is our new tagline. So we're primarily an IC company that designs, manufactures, markets things. We have, including the LTC acquisition, $5 billion of revenue. And that may seem like a big number. until you compare it to other like S&P 500 companies like Apple, $260 billion company. McDonald's, they make $6 billion a quarter. So, we're like a medium-sized company, I think. So Analog Devices is a great place to be an engineer. We're very industry recognized, one of lots of awards and continue to. And when you look at where we make our money, like 20% is communications, 20% consumers, 16% automotive, and 40% is industrial, including healthcare. And communications, especially the communications problems, transverse almost every industry. So the automotive guys are interested in car-to-car communications, which is working with some medical customers. The biggest single point of failure in an MRI machine is the cable that goes from the MRI machine to the system that does all the diagnostics. So they want to replace those with RF links. And if you're talking large bandwidth, lots amount of data, it's an MRI machine. And so we are like #1 in converters, #2 in power management, #2 in amplifiers, #1 in RF and microwave, #2 in interface. And we are kind of moving from this IC to subsystem to full subsystem solutions. And one of those places would be like the Analog Devices RF SOM. So this includes the 9361, which has the 200 kilohertz to 56 megahertz radio, Xilinx Zinc. So this, we have two options, one with a 7035, one with a 7020. And these are like production ready to go kinds of systems, where people will take these and put them in their end product. And they don't have to worry about DDR3. They don't have to worry about the serial flash. They don't have to worry about the Ethernet 5 because it's all built into the module. It just plugs down onto a carrier. And we've done some of these characters. We did like a large FMC carrier and a small breakout one with the pins. And then the first question you get is, okay, well, I'm designing a PCIe card. Can you help me with the PCIe drivers? Or how does this really work from a thermal standpoint? Because this is like 5 to 10 watts. And like, how does my enclosure work? And those kinds of things. So some of the things we're working on is like a PCIe card to show people from a device driver standpoint how to get it running. And does the device driver run on the host, or does it run on the ARM, or how does that get segmented? The RF SOM in a box is this system right here that we were showing at the demo floor if you hadn't had a chance to see it. It's actually pretty cool. We actually have a full modem running, a QPSK modem running inside here, untethered, so we can plug in a USB camera, transmit the data with FFmpeg because it terminates in the Linux side as TUN-TAP, and then we grab it on the other side and display it on the little screen here. It includes power over Ethernet, an automotive DC to DC converter, so the 12 volts is basically 5 to 60 volts, battery management, power swap, so you can hot swap all these things and still have the battery backed up. IMU, GPS, audio, real-time clock, and some of the devices, some of the devices in here are not ADIs. We don't make GPS chipsets, so we have to go buy somebody and get it from somebody else, or real-time clocks are the same thing. Just like everybody else would. So, it all fits together, it works in the box, and it shows people how to design their thermals and those kinds of things. And we kind of look at it as actually just a large power solution, because it is the power supply design for these kinds of things is actually pretty complex. We are hiring, and we have lots of hardware guys, lots of chip guys, and that's actually not where we need the most help. We need the most help in like system engineering, software architecture, wireless system architecture, software engineers, software design engineers, those kinds of things. We have 85 positions across the US open, and we are actually hiring for comms people and wireless system architects and power amplifier architects and these kinds of things. So if you're interested in those, you can definitely come by and talk to me, and I'll tell you to go check out the website, because I don't know where any of these positions are. So anyway, thanks very much.
Any questions for Robin? Phil?
Yeah. So the pricing on Pluto, is that a subsidized price?
No.
Okay. All right.
No, I pay Xilinx. I actually pay our own internal guys. I think, yeah, cheaper. I know customers get the parts cheaper.
Can you go set up?
Hey, so that RF SOM, I think it used to be like Pico's at SDR or something like that, and the business relationships changed. So is that still a thing, or is it like end of life? Because it's...
It used to be known as the Pico's at SDR, and now it is the Analog Devices RF SOM.
Okay, so it's sold through you guys.
We will continue to sell it, and we will sell it through our remaining distributors. So Arrow will sell it, DigiKey will sell it, Mauser will sell it. Thanks. Yep, no problem.
Are you only hiring citizens?
Most of it depends what it is. Like our Linux development is actually in Germany. We're hiring people there. For our Mill Arrow stuff, it's mostly a requirement to be a U.S. citizens. But we have the team that works for me is split between Philippines, Munich, Germany, Romania, Boston, and California. So it makes calls with aerospace defense customers super interesting.
Okay.
Thanks.
Mike Ossmann, everyone.
Is this thing on? All right. All right, spectrum visualization with the inverse FFT. I'm Michael Ossmann of Gray Sky Gadgets. We make HackRF and stuff. This is not me. Just want to make that very clear. But thank you to the Daily Mail for taking awesome photographs. I want to talk about spectrum monitoring and a little visualization trick that we've done. I gave a talk with Dominic Spill at Black Hat USA this summer. And if you want a lot more detail on what we're doing, I recommend that. It should be up on video soon. And also there's a white paper on the Black Hat website. But yeah, sorry. I don't know. I mean, do you want me to take time to try to fix that? Because no, okay. So deal with it. Anyway, we've come up with this solution, and this is some work mostly done by me and Dominic Spill and Mike Walters, whom many of you know from the Inspectrum project. The three of us came up with this solution for doing wideband sweeping very rapidly with HackRF for the purpose of spectrum monitoring. And this plot just kind of shows you how a traditional spectrum analyzer functions, right? It sweeps across a wide range of frequencies, does it fairly rapidly, and thereby measures the power detected on a wide range of frequencies. But it doesn't measure all frequencies all the time, right? Unless you get a very expensive real-time spectrum analyzer, which I'm not really talking about here. You're going to find that any really wideband spectrum monitoring solution, even benchtop spectrum analyzers, have some things that they miss that are kind of between these sweeps. And there's the more modern approach is to kind of digitally sweep or sweep in steps. And we should be able to do that no problem with any of our SDR platforms that we have available to us today. And what we were looking at with HackRF, the three of us, was, well, how can we maximize the amount of information we get in a spectrum monitoring solution and kind of minimize the gaps between those sweeps? And the thing that we came up with was that of the various parameters that affect kind of how full the spectrum is or how full this two-dimensional area is with data, the thing that we can really optimize is tuning time. And the way that we optimize that with our HackRF sweep solution is by putting the sweep function in firmware so that you don't have to issue USB commands every time you want to tune to a new step along the sweep. This dramatically increases things. We're able to sweep at a sweep rate of 8 gigahertz per second. 8 gigahertz per second, really, really fast. Okay, not super fast compared to benchtop test equipment, but for a $300 platform, we think it's pretty great. So I want to show you just a quick demo of that in Q Spectrum Analyzer. Q Spectrum Analyzer is a piece of software we didn't write. It was created for the RTL Power solution originally. And for those of you who have actually run RTL Power before, let me just kind of give you a look at HackRF Sweep. If you just run HackRF Sweep with no options, it gives you output that's very similar to RTL Power. Only right now I'm sweeping across 6 gigahertz of bandwidth, and every time you see the screen kind of flicker, it's because it's doing a new sweep. So really fast. But let me run Q Spectrum Analyzer and just show you a quick demo before I move on to the visualization trick that I'm really here to talk about. Here I'm just sweeping across 100 megahertz of bandwidth in the 2.4 gigahertz band. And so you can see we can get pretty useful spectrum analysis, even though our radio is really only tuned to 20 megahertz chunks at a time. But you might notice there's some interesting things here. Like you can easily see these three prominent Wi-Fi channels, but do you notice how things are kind of carved up into funny little 5 megahertz slices? You see how there's little gaps and things? Up here, if you look at the peak hold, it looks pretty clean. But if you look at any given instant of time or any horizontal row in this waterfall plot, you might notice some funny things. Also, those of you who have done the CTF, can notice something in between a couple of these Wi-Fi channels that I'm sure you've seen before. And let me just do real quick 6 gigahertz wide view, and it looks something like this. It's slower, of course, but we sweep about once every 3/4 of a second, and you can just use it like a spectrum analyzer, this sort of thing. Okay, so why do we have those funny little defects every 5 megahertz? It's because we actually are trying to get rid of other defects. Specifically, what we do is we take 2 overlapping or interleaved frequency hops, and then we throw out some of the FFT bins from each one. We throw out a chunk in the middle so that we get rid of the DC spike, and then we throw out a chunk on either edge to get rid of the anti-aliasing filter roll-off. And then, so really we take 2 20 megahertz chunks, we pull a pair of 5 megahertz chunks out of each of those and interleave them. And so that gives us some funny little things where like a Wi-Fi packet shows up in every other 5 megahertz bin, but since it's a transient event, it doesn't show up in the interleaved bins. But it does give us, over time, a much flatter response across all the spectrum that we're monitoring. So we like this approach. Now, here's the real trick that I'm here to talk about, and that is how can we visualize this kind of data in more interesting ways. And one of the things that Dominic and I wanted to do was we said, hey, Q Spectrum Analyzer is kind of cool, but there are other visualization tools that we like better. For example, phosphor. And phosphor, it just looks so pretty. We want to put our data into phosphor. How can we do that? And one of the ways we thought of was, well, we could hack up phosphor and we can get it to not do the FFTs, and we can feed our spectrum data into it and just use it for visualization and nothing else. But it kind of looked like it'd be a bit hacky and a bunch of work, and I had this idea that maybe we could just feed time domain information into phosphor and not modify phosphor at all. So we came up with this approach like this. We take interleaved hops on the left there, upper left, we convert them into the frequency domain with FFTs, and then we just stitch all those FFTs together into one long set of frequency bins, and then run that through the inverse FFT. Okay, this sounds really crazy, right? Because we're going to take a bunch of FFTs, and then we're going to run it through the inverse FFT so that we could feed this data to phosphor, which is going to run forward FFTs again to visualize for us, right? Sounds completely idiotic, but it works. And the really cool benefit of this is that we didn't have to modify phosphor at all, and we don't have to modify any other tool that knows how to analyze time domain signals. We can feed our HackRF sweep data into any software that knows how to analyze time domain signals. And we think that's a really cool trick and a useful trick. So what we end up with on the right-hand side there is a simulated a high sample rate. So if we're sweeping across 6 gigahertz of bandwidth, we get a simulated 6 gigasample per second signal. A short chunk at 6 gigasamples per second. And then 3/4 of a second later, we get another short chunk of samples at 6 gigasamples per second. And let me just show you a demo of what this looks like. So I should have a FIFO created. I do. And I'll just start GNU Radio Companion. If I can type GNU Radio, there it is. And I'm going to make a little flow graph, or I may have a little flow graph, like, don't I have something called phosphor? There it is, phosphor sweep. Okay, so not much to this flow graph. I'm going to take a file source of this temp pipe and dump it into a phosphor sink. And I'm going to tell phosphor that I have a sample rate of 6 gigasamples per second. And I'll start that flow graph, and then I'll start HackRF sweep and like feed it some data. That should be good. It'll take a second to start up because of the inverse FFT. We're using FFTW, and it takes a second for FFTW to get started when you give it a whole lot of frequency bins. Okay, so this is 6 gigahertz wide. This right here is the 2.4 gigahertz band, right? So we get quite a bit of activity there. And there we go. We're using phosphor 6 gigahertz wide and telling phosphor we have 6 gigasamples per second. Of course we don't, because if we really did, these little bursts that we're seeing would be separated by a tremendous amount of blank space, or this thing would be scrolling by so fast. But since we're getting only a very short burst of samples every 3/4 of a second, it looks something like this. So we're totally abusing phosphor here. Like, one of the things I always tell people is so great about phosphor is that it lets you see everything that's going on in this bandwidth, and you don't miss stuff, and transient events show up, and it's so wonderful that way. So we're completely, I'm afraid that Sylvain probably hates us for this, but, oh yeah, he's nodding his head. He hates us for this. Yeah. But let me show you what this looks like here with just in the 2.4 gigahertz band. Our default bin size is 1 megahertz. So let me show it to you with the default bin size, and I'll just go into my flow graph and tell phosphor that we have like 100 megasamples per second in the 2.4 gigahertz band, and start it up and feed some data into that pipe. And this is what it looks like with our default bin size. But it turns out that when we use our default bin size, we're actually collecting a bunch of samples that we're throwing away. So if we use all those samples without throwing them away, we can just use a smaller bin size and get it to look something like this. Now I'm going to use something close to our minimum bin size, which is maximizing the number of samples that we're using. It goes a lot faster because we're just getting more data. More of the data that we're collecting is finding its way into phosphor. And I think, even though we're totally abusing phosphor here, I think this is super useful because visually, you can really see what's going on in the 2.4 gigahertz band here. I mean, and even though we have those funny little 5 megahertz chunks that may look a little bit different from each other at any given moment in time, if you look at the general trends, which phosphor does a fantastic job of showing us up top, you can really see things like the shape of the modulation, the spectral footprint of the Wi-Fi channels and the spectral footprint of this thing that the CTF players know about, and so forth. And that's it. Any questions? Any verbal abuse? No? I thought for sure I'd at least get that. What's that? Plenty of abuse in chat. Plenty of abuse? All right.
Okay, we have a slight change of order. I don't know if Alex Jamaris is here even.
I think Robin has.
Okay, Marcus, can you just go set up? I can't even see the next speaker according to the schedule.
Take advantage of the AGC or the gain to increase your dynamic range across, or you just set up for manual mode across the whole range?
Oh, that's a good question. Can we do AGC and like try to normalize our gain across the wide range? Theoretically, we could do something like that, but we haven't. We just have our analog gains fixed at this point, and yeah, we haven't made any effort to do that. But that is something that we could theoretically do in firmware. We do.
You need to tag every buffer, I guess, with what the gain setting is.
Right. Yeah.
Manipulate that in software later.
Right. We could throw in a little metadata. We already are throwing in a teeny bit of metadata into the stream that's coming over USB here. Mostly, we're sending time domain samples over USB, just like we normally do in a HackRF receive operation, right? Except they're coming in blocks that are tagged with a little bit of metadata that tells us, what frequency it's tuned to. So theoretically, yes, we could add some metadata to that gives us some information about like the gain configuration or any other configuration parameters that may be either automatically determined or pulled out of a table or something like that for calibration purposes. We haven't done that, but yeah, it's something that could be done.
Yeah, that will allow you to compensate for any roll-off in the high end and low end, and I'm sure it's in the hardware too. So to linearize everything.
Yeah, right. Linearization, that would be a good thing. Thank you, Robin. All right, thanks, y'all. Oh, one more question? Sure. When can you use it? Oh yeah, HackRF Sweep is in the most recent release, in the February release. So you can download, if you download the latest release, and you do need to do a firmware update, but that's in there. The inverse FFT trick has not made it into a release, but it probably will. But it is in Git. So if you just take the Git, and you don't have to, if I remember correctly, you don't actually have to update your firmware to Git. You can be running the 2017 February firmware. You just need the host code from Git because that's where we're doing the inverse FFTs.
Okay, so are you ready, Marcus? Do you have the clip-on mic?
No, so I'm not ready. So, does it work?
I think it's turned off. At the top, dip switch. There you go.
So, hi and welcome to my chaotic 5 minutes about generator scheduling. So this is 5 minutes and I needed a way to time things. So I kind of forgot to turn this on. So I actually have Brent running in parallel here in a speeded up version, so I have a time. All right. So what's this talk going to be about? This is not interesting if you went to my tutorial and understood everything, but it is interesting if you always wanted to know, okay, how does the generator scheduler roughly work without like reading through Tom's presentation that's a little bit longer than this. So I'm going to go through buffer scheduling and other scheduling things, and let's start with something that I always wanted to say. Do always memorize my important truths slide, which is basically don't use throttle. Unless you know what you're doing, don't use throttle. Because like half of the flow graphs that actually have some problem with overflows, underflows, other hardware shenanigans, they just try to like throttle something and pipe it into an audio sync or throttle something that comes out of like a USB source or something. Don't do that. Throttle is not your friend. Throttle doesn't do anything to the signal. It just like slows down the average rate at which like samples are passed from the input to the output, and that doesn't do anything. So don't use throttle. Never use throttle unless you're actually like in a simulation or in like a playback scenario where you want to slow down what's happening on your screen. That's like the only exception there is. Don't use throttle. So back to scheduling. So what is a flow graph? A flow graph in GNRadio is really just a bunch of blocks. Blocks are like C++ classes that have like a work function, and they're like logically connected by these nice little stream connectors. And what physically or technologically connects them is actually buffers. And buffers is kind of surprising because if you like this, we call these stream ports, right? So this is not a stream, it's a ring buffer. So let's talk about ring buffers. So GNRadio's ring buffers is really like not really a ring buffer, it's just like a memory trick to double map the same memory twice and then always read linearly, even if you're like going across the boundary of the original buffer. And I do happen to have like a blog post on our website with the URL down on the slide. So if you're interested in that, please go there and write me emails, angry emails. The advantage of that is that there's no one actually like mallocing memory, writing their samples into it, sending it to the next block, who then uses these samples, frees these blocks. Because mallocing, memory pooling, this is kind of things that happen to have unbounded complexity if things aren't really aligned. So we avoid that, which is really, really nice because we get like linear memory in every work call, and which is very nice when you're developing algorithms because you don't have to like write your algorithm with the fact in mind that the things you're working on aren't actually linear in memory. So this is very nice for the algorithmic efficiency of your algorithm, but it's not as nice for latency, which especially becomes obvious when we think about, okay, how how do blocks that have multiple readers on their output coordinate axis? It's actually, we have a ring buffer, there's this write pointer that moves forward every time my work produces something, but there's also like the downstream blocks consuming data, and only when they have consumed data, they move their read pointers forward. And my write pointer obviously mustn't ever overtake the read pointers, because in that case, I'm overriding something that someone else hasn't already consumed. And so that mustn't happen. And obviously, that kind of limits the throughput in your flow graph to the slowest link in the chain if you do that. Again, this is just how GNRadio always has worked. And it's kind of working very well for the sample business. It's not working that much well for other things like passing packetized data, but we'll come to that later. So how does that whole, okay, I execute my work function occasionally work? And what we have these days is the thread per block scheduler, short TPB. And we used to have the single thread scheduler back in the day that has been like defunctional for years now. It's been pretty much removed from 3.8, so you can't use that anymore. We call it a scheduler. It's not actually a scheduler. The scheduler is in the Linux kernel. We just like assign a thread to every block executor. For every block has Getz its own thread. And so I'm running out of time, but I'm going to speed up here, if that is possible at all. So what happens is that every block has its own block executor, which runs in its own thread, which is just a loop, and if a block is done, it notifies the others, like the upstream and downstream block, depending. Which is nice for the complexity, but not as nice for like latency again. Because let's look at that loop. So there should be a block in the first sentence, but so the work function is executed when the loop detects that there's either both enough input samples to do something for the block and enough output space for the block to write it to. So if that's not given, like the loop simply blocks, and we're basically the block is idling, and other blocks take over the CPU, like are scheduled by Linux or like operating system, and so that's if we have enough. This is the way that multiple blocks run in parallel. If it's scheduled, it calls the work function. The work function does its work, so it takes the data from the read pointer. It's attached to the input buffer, which is the output buffer of the upstream block. There is no dedicated input buffers. There's only output buffers. This is kind of important to realize. And if it's done, it advances the read pointer, and it advances the output write pointer because it has produced samples, ideally. So yeah, so that's how this whole scheduling works. So what are the emerging properties of that? That is basically all blocks can actually run in parallel if you have enough CPU cores, which is great because that means like, okay, we're getting the parallelism for free, and it turned out for the last couple of years that this is a really good generalized concept. We have seen this GRCon. This is actually the first time that we had someone investigate, like as far as I know, someone investigate that it's really like easy to do something smarter than just letting Linux decide on, okay, when to schedule what. But it has turned out that this is a pretty solid concept, and so I'm thankful for like operating systems being smart. It also means that this whole radio flow graph is back pressure limited. So this is not something that passes a message from the input to the output and to the output to the output as fast as possible. It's just like it works as fast as possible, and it's always the back pressure that limits it. So if your sync is the slowest thing, then the buffers will fill up, leading to that, like in every block upstream, the buffers will fill up, and so you get a lot of buffering, which is like the latency you notice if you're writing a complex modem. But it also means that if you're having a complex flow graph with like jittering latencies, that doesn't mean that your USP source is always overflowing, because you still have a lot of input buffer to fill up until things really get congested if you're on average fast enough. Which is again nice for throughput, but not as nice for latency. So now we're in the other scary things domain. There's the tags. Tags aren't actually like in-band. There's not like the sample stream, and then there's tag info in between. It's like the sample stream is raw data in RAM, and we have a vector or a standard map containing the tags. They are ordered, and if you do a get tags and range, you just actually get the tags from the vector. There's no in-band signaling, which is kind of nice because we don't have to like tell data apart from metadata. But it also means that there is overhead involved with having tags. So these need to be purged at some point if they like propagated out of their scope. If like the read pointer has passed the index of the tag, then it has to be removed from the system. So this is a non-free operation. It's getting relatively performant, but please don't try to have a tag on every single sample. Yeah, so Martin is having strange faces. I should probably not be talking much longer. So then there's message passing, which is more like, actually feels more like a stream, because you can actually push things out. And that is basically used for packetized data, settings and stuff. And what happens is that whenever your block is not executing a work function, it checks for messages basically and calls the appropriate message handler. And that means you're basically thread safe. You see, every block runs in their own thread, and if you're like a fur filter and someone calls you, okay, let's update my tabs function, you might actually be host, because that's not a nice thing if like the number of tabs change, and then you probably want to have thread safety. So if you're writing something that actually isn't thread safe to modify while work is executing, I'd strongly recommend having a message handler registered and being sure that your users like send messages instead of like directly trying to interfere with your state. So that's my talk.
Any questions? Most distracting timer ever.
Thanks. I was actually trying to achieve that.
What's more gory, brain dead or the scheduler code?
I mean, have you actually read block executor CC?
Yes, I have. And then I also watched Brain Dead to calm me down again.
Yeah.
So we have two more. I mean, we have plenty more, but we'll do two more lightning talks. First Sam, and then Maitland, and then we'll actually take a quick 10-minute break where we can, refill our coffee cups and all that. So is Maitland here?
So,
Okay, well, Maitland, wherever you are, you're up next after Samantha.
what's the command for full screen? F11?
I'm sorry?
Oh, or not. Oh, yeah. Now I see what the whole problem was with everyone. What?
You don't? Maybe find it out.
Let's see if I can. Ugh. Yes. What? Like document? I guess this is fine, right? Maybe. How do I?
Try the 5.
F5. Try something else. There. Okay. So this is kind of a rehash of a talk I gave previously, and I'm going to skip over most of the stuff because of the audience. It's a little bit different. But this is using software-defined radio to analyze IoT devices or Internet of Things devices. And so specifically, this is, let's see. This is specifically for devices that kind of have their own protocol. They don't necessarily know, like Zigbee and Z-Wave and things like that. So we'll just go through the steps. One of the things I kind of wanted to share with the audience here in particular, actually, I have a quick question. Is anyone here relatively new to GNU Radio? Really? Okay, so this is kind of a perspective for that. One of the things that was really important is that coming to these conferences and talking to people is really what gave me the ability to do this kind of analysis on my own. I didn't have to go through a huge slog of understanding, all of DSP and exactly how things worked in order to get things done. So these are basically the steps for that I would follow in analyzing a typical IoT device. Gathering information, I think, kind of makes sense, the FCC data, all of that, and also finding other tools. Like, has anyone else in online, in the GNU Radio community in particular, already worked with this stuff to save problems, or to save time? Right, so kind of a standard communications chart and stepping through. The idea with this is that you don't need to make it, there's a lot more to dealing with RF signals and decoding and demodulating, but trying to break things down to the kind of littlest amount as possible. So I like to use GQRX to capture data. And one of the things that is really in particular with IoT devices is that one of the first things I always check is to see if replay is possible, because a lot of these devices are kind of notorious for just having awful security and awful implementations. And so this is an example of this particular door lock is vulnerable to a replay attack when you add it into a greater ecosystem. So the door lock itself isn't the issue. They'd probably implement some kind of rolling code that you could still probably crack. But in terms of, like, all you have to do is record it and play it back, and you can unlock and lock a door. It's kind of a not the greatest issue. So ever since discovering this particular thing, I'm like, anytime I get an IoT device, it's the first thing I check, because there's still a chance that someone somewhere decided not to check this. Right, so I found InSpectrum is a really great tool for looking at the signal and checking to see if when you demodulate something, it looks like the signal that you're expecting. You can see the ones and zeros. Right, so this is really cool, and I have to give Michael Ossmann a lot of credit, because this is what you showed me at the last GRCon, for being able to take a signal and then kind of parse it into the bursts of information. Because I had to do this because I wanted to use your whole clock recovery tool, which I didn't end up using. So here you are at the last GRCon when you presented this. This saved me a lot of time and a lot of pain. And I think that's what's really great about this community is that you don't necessarily have to do everything on your own. There's a good chance that someone somewhere has dealt with the same problem as you and that you can find a tool that will save you, yeah, like I said, it'll save you a lot of time. And it can be kind of really unexpected. I love these conferences for that. You always end up finding something you're like, oh, I needed that. Or maybe 6 months later, you're like, I remember something about this at GRCon that will save me a lot of time. So in this case, I was able to get the bits. And it turned out that this particular protocol, they had documentation about how it worked, but it turns out that the documentation of, I guess their API or whatever that you could find was not the greatest, wasn't quite to spec, so it was kind of random. But it also turns out that there was another tool that was shown at DEF CON a few years ago. And for this particular tool, I had tried originally to get it to work, and couldn't get to work, and I had set it aside. And I was like, I don't know. But when I was able to get the bits using the clock recovery tool, then I was able to take that information and kind of spit it into this. And so it's kind of like a piecemeal process, because I'm not particularly fond of doing any developing or coding on my own, but was able to work through this and to receive the data that was originally sent. So I guess, and I can't read what I put up there, but I think the point is that the GNU radio community has really started to lower the level of understanding of some of the DSP to do these analyses on various devices like this, and it's really useful. And I really appreciate the community and the work that is done. And I guess this is kind of an example that when you put your work out there, it will end up being used by someone, or there's a good chance it will end up being used by someone else who maybe is not as capable as writing that back-end code as you are. So that's it.
Okay, thanks. Maitland Bottoms is next. And do we have any questions, real quick? All right, Maitland.
Yes, you do. Here you are.
All right, so if I don't get video, just go over to freedv.org, freedv.org. But we'll see. Magic display stuff. We'll just mirror this. That look good? We'll keep the changes. All right, so FreeDV. Bruce Perrins was brought up that he's developing codec 2 and the FreeDV for using low bit rate speech codecs in amateur radio. For a couple of years, I helped out at the Hamvention in Dayton. I didn't do so much in Xenia this year, but trying to sell people on using it. And a lot of hams have done digital modes. So they've already connected radios, and by radios I don't mean software ones. So they connect the sound cards to their radios and interfaces for making it transmit and receive, switching and all that. And so they got radios, computers, sound cards already connected up. They're doing PSK31, data modes, having a great time. And I tell them, and first of all, a lot more hams have actually done that than I thought. I see random old guys thinking they'll never do a PSK31 digital mode. And I say, have you tried this? They said, oh yeah, it's my favorite mode. It's very popular. So a lot of people have this capability, and I said, okay, well, you need to do FreeDV. It's a digital voice mode. The only thing different from the data modes is you need a sound card for your mouth and your ears. And thanks to gamers, you can go to Walmart on a Sunday afternoon and buy a USB headset for $12. So the barrier to entry is low in the community. And so it's kind of boring because I don't have a radio connected to this. So, actually running FreeDV is just not that exciting. If I hit start, it's got like no audio. There should be a beautiful waterfall here, but everyone's been seeing waterfalls all week. So there's a thing on the freedv.org site. Think back 60 years ago in amateur radio, there was like, people were using vacuum tube transmitters and AM was king. Everybody talked amplitude modulation. And this revolution came, it's called single sideband. You needed more stable oscillators to tune it in. And it was a revolution because it had half the bandwidth to communicate than AM. It was a revolution. Would that ever happen again? Well, in our lifetime now, it has. Due to the 700, the low bitrate codecs, the bandwidth of this waterfall is half the bandwidth of single sideband. So we've had yet again another bandwidth efficiency revolution in radio communications. And David Rose doing this is a great development. All you hams should go do this. That was my spiel that I would tell all the ham radio operators. I need to tie in some GNU radio applicability here. In my Debian packages, I add some codec stuff that I've been fixing. It's in the GNU Radio Next branch, because last year we got this fixed up and submitted to GNU Radio with updated codec 2 blocks that will now interoperate. The old codec 2 things in GNU Radio were just bit rotted and diverged from what David Rowe was doing. And so here's a flow graph with a codec 2, and it's got all these nice things. And let's see, I think I didn't connect audio. I'll do audio. So the flow graph is really just getting a wave file and running it through the codec low bit rate thing and playing it out the speaker with some sample sounds. So this is 700 bits per second audio. So if you look on the flow graph between this encoder, the codec 2 audio encoder, and the audio decoder, I'll turn that off. Between those two, implement your radio. There we go. So the deal is the FreeDV stuff has blocks that are built into the codec 2 library, actually, that take your audio signal and convert them to another audio signal which goes out the radio. And so that would be this FreeDV API block. And if you do that, it's all real signals, so I got plus and minus things. But if you do this little thing with just taking some audio, modulating it, and you can see the spectrum, you could probably add a little GUI elements and re-implement the traditional FreeDV API. That is what I had to tell you guys. Build a radio between a FreeDV modulator or build a radio in between this low bitrate audio and have fun. Thank you.
Okay, we'll do a quick. Oh no, we have questions. Yeah, go ahead.
Sorry. So first of all, this is super cool. I mean, we have to agree that 700 bits per second.
700 bits per second. Yeah, that's what you're listening to.
I actually have a non-published kind of broken auditory module that Brent's radio streams on Twitter accounts, because Twitter is great at it.
Yep.
But you need just 15 of these to have understandable voice.
In real time? I mean,
yeah, no.
Lot of latency. Actually, because you was talking so much, I'll just give you the mic.
Yeah.
was going to repeat the question, but it's not actually a question.
So can you tell us a bit, like, the OFDM modulation of 3dB? It's like 16 carriers, 14? Or?
Oh yeah, so there's a central clocking, timing thing that's louder than the rest, and then 14 other carriers. And I don't know the details, and I never really implemented it using standard GNU radio blocks. So David Rowe did that all for us, and so there's a FreeDV API, so I put a block around that, and it's all done in one place. But yes, experimentation would be cool. I'd love to have David Rowe playing with GNU radio instead of all of his Octave scripts. But, you know, he does awesome things anyway, and the rest of us can do it in GNU radio, and, you know, hopefully this helps a little bit. But, yeah, there's different things, and so there's been like no big forward error correction thing. The interesting thing about this waterfall is as you get multipath and fading, and you lose little bits of audio, because you don't have to wait for some FEC correction, your ear integrates the little gotchas and bursts and stuff. And so it is like a real-time mode, and like other sideband signals can come in and destroy it, and then it just pops right back. You know, 30 milliseconds later, you've got another correctly decoded packet. So it is really, it's just, if you're used to those old-fashioned digital modes that just took several seconds before actual output happened, this like very low delay stuff is so cool.
Anyone else? Okay, I said we'll take a quick break. 10:50, we'll start. Next speaker is Philip. And after that, it's Nate. So just so you know.